Hi, my name is Kautz. I lead the learning and perception research team here at NVIDIA, where my team specializes in AI-based perception. And today I'd like to talk about a few recent research projects on using AI to perceive humans. So, perceiving the human body is of great interest for many practical applications. For example, these methods can be used in humanoid robots that actually interact with humans, or for self-driving cars to understand their surroundings. You can also use them for monitoring humans, such as to automatically generate alarms in case of an emergency, or we could use it for sports analytics, but it can be used to create game statistics and personalized training and so forth. So given all these different potential applications, we've spent quite a bit of time in this domain. In particular, I'd like to talk about 3D pose estimation from RGB-only images, and then how we can use that 3D pose to articulate a human body mesh. I will also show how we can deal with occlusions and moving cameras. And then once we know everything about the body, we will also estimate the 3D hand pose. So let's start with a 3D human pose estimation. And here, by 3D body pose estimation, I mean the localization of human body joints in the 2D image space, as well as in 3D with respect to the camera. Having a fiducial method with this ability has lots of practical applications. For example, at NVIDIA, we've been using it to let people stride across the moon's surface, which was a demo a few years ago at SIGGRAPH, or in Omniverse Machinima, you might want to drive a character from a webcam's feed, for instance. So our goal is to train a model, which of course is a neural network that takes an image of a pre-localized person, so we already have a bounding box in 2D, and then produce the 2D as well as 3D positions of all the body joints as the output. This is a very challenging problem, specifically the 3D localization part, because it's inherently an ill-posed problem. First, it's ill-posed because of the scale and the depth ambiguity. That is, there's many different 3D configurations that might yield the same 2D projection on your screen. So if you don't know the size of the person, it's hard to determine how far they are from the camera. Here's an example where there's two different scenes of a person with different scale and depth, but they project the same 2D image. And this one-to-many mapping makes the problem very ambiguous. Second, in order to train a convolutional network, we need lots of training data. In this case, training images with accurate 3D pose annotations, because we want to predict not just the 2D locations in the image, but also the 3D world positions, or at least relative to depth in camera coordinates. Now, collecting such training data is actually really difficult and time-consuming because it requires sophisticated hardware setups, motion capture system, and the like. And as a result, collected data is often limited to control indoor environments. So they're not natural environments. As a result, it might not work outdoors. And of course, it's difficult to scale, right? How do you easily acquire lots and lots of people in such a capture setup? Now, there are two main approaches for training a pose network. One, we directly regress the 3D pose from an image. So you really go from image neural network to output the 3D coordinates of all the joints. Now, since such a model would be trained using very constrained images, such as the ones acquired in a motion capture setup, it's difficult for a network trained in such a way to generalize to unconstrained scenarios. Also, in order to reduce the 2D to 3D ambiguity, existing methods only estimate relative 3D pose and neglect the absolute 3D translation of the person, because that's difficult to judge. Also, if you do it with this direct regression from image to 3D, it's really decoupled from the 2D image, if you will, right? You don't know where the 2D locations of the joints in the image are, so you can't double check whether they're sensible or not, the 3D ones. So it has some real downsides to this approach. Another possible approach is to train a model that first outputs just 2D locations of the key points, and then you take those 2D poses as input and try and lift it to 3D. 2D pose estimations work better, or can work better within the wild images, because we can label lots of 2D images by hand with 2D joint positions, which is difficult to do for 3D, right? Labeling in 3D would be really difficult for a human, but labeling the joint locations in 2D is actually quite possible. So as a result, such a method has a better ability or capability to generalize to unconstrained setups, because lifting something from just a 2D location to 3D is independent of what the appearance of the image or video looks like. There's still some constraints or limitations, such as redirection ambiguities are still difficult to deal with. For instance, in this case, we don't know whether it's the person is looking to the right and we're looking at it from the back, or the other way around. Right? We would need to look at the image itself to determine what the actual orientation is. So our goal is to develop an approach that generalizes well to unconstrained environments. So arbitrary images and arbitrary scenes. We want to be able to handle some of the redirection ambiguities, and we want to be able to provide absolute 3D pose so that the result of this pose estimation can be used for animation. So to this end, we've proposed a novel 2.5D pose representation that satisfies all of these requirements. So it's invariant to 3D scale and translation, so it's less ambiguous to estimate. We can exploit multiple sources of training data, that is 2D labels as well as 3D labels to exist, so it allows for better generalization. And it does enable exact 3D reconstruction to get absolute 3D pose. So our pipeline is as follows. We have an image, just RGB. We first estimate 2.5D pose using a neural network, and I'll explain what 2.5D means here in a second. We then devise an exact method to reconstruct the 3D pose from the 2.5D representation. And then we recover the correct scale of the person, which gives us our target absolute 3D body pose. Now, let's see what we mean here by the 2.5D pose representation. So here's the equation for perspective projection from 3D locations onto your 2D image. The capital X, Y, Z are the 3D coordinates of a particular body joint in case of camera matrix, and the lower case X and Y are the 2D projections. We represent the 2.5D pose using the 2D coordinates of the pixels in the image space. But then for the depth, we don't use absolute depth, but we use what we call root relative depth. That is, it's a depth value with respect to a particular root joint. And we get to pick which one we want to use. We usually consider the torso of the person as the root joint, and all the other depths of all the other joints are relative to the torso. Now, using this relative depth representation means that our 2.5D representation is really invariant to the 3D translation of the person, right? So it doesn't matter if you're closer or further away, because we're just recording depth relative to your torso and not relative to anything outside of our control. Of course, we still need to make sure that it's invariant to the scale of the person to also reduce scale ambiguities. Now, for this, we do something very simple. We scale normalize the 3D pose such there is a fixed distance between a pair of key points, which brings all people to the same unit scale. So if a person is bigger, we make them smaller. If they're smaller, we make them bigger. Nothing, too surprising, really. Now, our final 2D pose representation looks like this. It consists of the 2D body joint coordinates, which are really well defined in the 2D image space, and then the scale normalized relative depth values, which are agnostic to the person's scale, as well as to the person's translation. So as a result, it's significantly less ambiguous to estimate this 2.5D pose representation compared to an absolute 3D pose representation. Now, instead of predicting the 3D coordinates, the model predicts the 2D pose, so 2D coordinates in image space, and the scale normalized relative depths that constitute our 2.5D pose. Splitting it like this has the advantage that we can actually use two different sources of training data, which is really great. So first, we can collect, or take a collection of in the wild images that are annotated with 2D poses. So for each joint, we have the 2D location, and we know which joint is which joint. And this is fairly easy to do in large numbers because people can label these fairly accurately. Secondly, we can have a collection of constrained in-there images that also have 3D pose annotations, such as for mocap images, from mocap system. Even though they're hard to get in large numbers, it's good to have at least sort of some of it, right? Now, during training, we optimize for a loss consisting of two terms. One is the 2D loss to make sure that we get the 2D locations in the image space, right? And then we have a depth loss to estimate whether the predicted relative depth is accurate or not. Now, and we sample an equal number of training images from both sources, meaning from the 2D pose annotations as well as for the 3D pose annotations. For images where we only have 2D pose annotations, we only compute the 2D loss and backward through that. The depth loss is considered to be 0 here because we have no depth, right? And then for images where we have 3D pose annotations, we compute both losses, right? Because we can project the 3D onto the 2D image, so we get both the 2D coordinates as well as the relative 3D coordinate. And we can compute both losses and backpropagate the gradients through the entire network. Now, jointly training using both sources allows the model to be trained on very diverse images, and hence it leads to much better generalizability, which is what our main goal really was. So this is great. Now, we also want to look at the neural network itself that we use for the 2.5D pose regression. So typical regression networks often consist just of a simple backbone model such as ResNet 50 or the like, followed by a fully connected layer to give our desired output. Now, in order to keep the complexity of the fully connected layer tractable, often we need to make sure that the resolution of the input features are fairly small. So for ResNet 50, that might mean that it gets downsampled 32 times to fulfill this. Now, this has the disadvantage that the model now immediately loses its ability to accurately localize body joints in the image because I've downsampled the spatial resolution. Now, I can learn the overall structure of the body well, but the body joints won't be at exact 2D locations. So instead, to alleviate this problem, the state-of-the-art methods for 2D pose estimation resort to fully convolutional neural networks and predict the 2D pose using a heat map representation. So during training, we use a ground theory with 2D annotations and create these heat maps by putting sort of Gaussian blobs centered at the true joint locations and supervise the network to produce these heat maps by a simple mean square error. So that's fairly straightforward. And we can do the same thing for the depth by creating sort of ground truth depth maps that have the correct depth value at the center of the Gaussian blob. Now, during inference, we get the estimated heat maps, and we take the 2D location with the highest value as the location of the body joint, right? It would be an argmax. And similarly, we can pick the depth value from the same location in the depth map. So that's actually fairly straightforward to do. However, it comes with a downside. In particular, the argmax operation is not differentiable, right? That means if you were to reconstruct a 3D pose from 2.5D, we can't apply any loss directly on the 3D pose, which isn't great. Not critical at the moment, but we'll see later on that it would be really useful to be able to do that. Furthermore, the ground truth heat maps are, in effect, hand designed, right? Because we're putting a Gaussian blob on them, which is not ideal because the spread of the heat maps is the same for all key points, where ideally it should be adapted for each key point, right? Heat maps should be very picky for places where it's easy to estimate the joint, such as for a wrist, right? It's relatively easy to pick out exactly where the wrist is. Whereas for the torso, it's much harder to pinpoint exactly where the joint should be. And as a result, the heat map should be, the blob should be wider for those locations. So ideally, we want to learn those instead of fixing them a priori. So to this end, we propose to learn the heat maps in a latent way and use soft argmax to go from heat maps to 2D joint locations in a fully differentiable way. So essentially, we take the latent heat maps produced by the network and apply softmax normalization to it and approximate the intuitive coordinates with the highest confidence value via soft art max. Right? Yeah, fairly straightforward. For the relative depth values, we take essentially the Hadamard product of the normalized heat maps and the latent depth maps, which zeroes out all the depth values that we don't need, except for those that are close to the body joint, and then we just average those to give us the actual depth, which is simple to do. And that gives us the relative scale normalized relative depth for each of the joints. So as a result, we can now get a 2.5D pose from these latent heat maps and depth maps in a fully differentiable manner, which is an advantage. Furthermore, if you look at the softmax normalization formula, we see that there's a parameter that controls the spread of the heat maps after normalization. And in our formulation, we've kept it as a learnable parameter during training, which now leads also to an optimal value for that, for each body joint type. So indeed, we can see what we already predicted should happen, that for joints that are easy to learn, it's a much more peaky distribution, whereas for other body parts such as the torso, we get a wider blob as a result, because it's a little bit more uncertain where the joint actually is. Now, this completes our full process for obtaining a 2.5D pose from an input image. So now we still need to go to 3D, right? Now, given the 2.5D pose, there's two more steps that we want to take, or that we have to take, to get our final absolute 3D pose, which is the 3D reconstruction from 2.5D and scale recovery. Now, to do the 3D reconstruction given a 2.5D pose, here shown in green, we need to find the depth Z root of the root key point, here shown in red, in order to reconstruct the scale normalized 3D pose. Now, there's many 3D poses that can have the same 2D projection, which means we can plug any value of Z root on the left side and it will give us some 3D coordinates on the right. However, given the relative depth and the intrinsic camera parameters and the knowledge that the distance between two key joints, it's a constant, there's a unique 3D pose that satisfies our scale normalization constraint, which leads to the following polynomial equation here, which we can just solve, giving us a solution or an exact solution for Z root. So now we have everything to reconstruct the scale normalized 3D body pose. And this brings us to the final step of recovering the scale in order to obtain the absolute 3D pose. Now, for this, we need to know the 3D distance between the torso and the pelvis, which are the two joints we've chosen, and in many practical applications that can either be known in advance, or if it's not available, we can estimate it by assuming what as an average human, what the value is for an average human, or we can minimize sort of the bone lengths of all joints for an average human, and the resulting scale value brings the bone lengths of the estimated pose as close as possible to that of an average person. So we can do it person specific or based on the average size of a person. And finally, this gives us our target absolute 3D pose. Now, in terms of accuracy, the method works really well, performs great on public benchmarks. It's published at a leading conference. However, there's still some challenges left to solve. In particular, as already mentioned, there are challenges around 3D training data. So, we started to think, what can we do to avoid the need for 3D annotations that come from mocap systems, which are really, really hard to get. So how can we train a model without 3D annotations? First, we identified that unlabeled multi-view data is a good source data that can possibly replace 3D annotations for us. And it can be easily acquired in any setup with just multiple static cameras that you place, or even with a single moving camera around static people. So here's an example of our simple setup. It's very easy. We can even collect this alone. So this is here, a couple of cameras placed in Umar's home, who's the main author of this work. And he's recording himself while doing some daily chores from 4 cameras in this case. So it's very easy to set up, and you can do this basically in the wild very, very easily for all kinds of use cases. Now, a simple way of utilizing unlabeled multi-view data for training is just via multi-view consistency, right? Instead of having ground truth labeled 3D data, we say, well, if you have multiple views, we want to make sure that our estimates are consistent across all the views. So, we process each camera view using the pose estimation model and supervise it to produce identical 3D poses from all camera views up to a rigid transformation, right? Because they are seen from different views. However, just naively enforcing multi-view consistency leads to degenerated solution, right? For example, network can very easily cheat by just producing all zeros or a mean pose from all camera views to satisfy the multi-view consistency constraint. That's, of course, not quite what we have in mind. Now, we avoid this problem by, again, adopting our 2.5D pose representation. So that gives us 2D pose and the scale normalized relative depth values. And as we mentioned before, the 3D pose can be reconstructed from the 2.5D pose, and this reconstruction process is fully differentiable. Hence, the multi-view consistency loss that we would like to apply can directly operate on the 3D poses because everything is differentiable. Right? And then during training, we can introduce a 2D loss that enables correct 2D pose predictions. So it can't lead to degenerate solutions because we have some 2D data and it needs to be consistent with that 2D data. So for simplicity, let's just assume that 2D loss to predict the 2D poses for each camera view are correct. And we only need to learn the correct relative depth values at this point. For this, we start to train the model jointly for both the 2D loss and the multi-view consistency loss. But since the 2D loss, the 2D poses are already correct, that was our assumption for a moment, the only way for the network to minimize the joint loss is to predict the correct relative depth values. Right? In addition, we used bone length loss, which forces bone length to lie in a plausible range and further constrains the solution space. So it's hard for the network to predict nonsensible things or try to cheat. And notably, we do not assume knowledge about the extrinsic camera parameters. Right? In cases where they're known, that's great, we can use them. But if they're unknown, we don't need to estimate them explicitly, but we rather do this on the fly using the estimated 3D poses, and we align them using Procrustes analysis, which is super convenient, right? Because now we can just put down cameras. We don't need to do any extrinsic camera calibration. So it'll be done sort of while we're training the network. It'll figure it out on its own by using the rigid alignment process in the loop. So here we show results for in the wild videos taken from YouTube. Notice that it works very well. Even the relative distance between people when there's multiple in a frame is very good, right? Because we estimate as well as we can the absolute position of each of them. So if there's people further away, we can actually figure this out. If there's people closer by, our method will automatically figure this out, which is really great to see. In terms of quantitative results, here's comparison to a bunch of different methods, all of them were state-of-the-art at the time. On the human 3.6M data set, which is our benchmark data set used for human pose estimation, our approach yields 16 and 70% error reduction as compared to other semi-weakly supervised methods, which is great. We've also used the mannequin challenge data set to train our method. So this is a data set that contains people who are not moving, but the camera is moving around them, or around them in parts, or translates, which is really a great data set that we can employ. And if we use data from this training set to train our network and then run it again on a human 3.6M data set, we have also a reduction in error of 11%, which is a very good result. So in conclusion, we've presented an approach for 3D human pose estimation from single RGB images. Our approach does not require 3D training data, but instead uses unlabeled multi-view data for training, which makes our approach really very practical, in particular for scenarios where it's difficult to collect 3D ground truth data. This is a perfect method to use. Also, our approach provides absolute 3D poses and yields state-of-the-art performance. Now, I'd like to move on to mesh articulation. Here, the goal is that we want to articulate a human body mesh according to the 3D pose observed in an image. Most of the existing methods that solve this task, that's going from an image to a 3D human mesh, adopt a regression-based approach where an encoder with a fully connected layer predicts the parameters of some parameterized body model, usually the SMPL body model. Now, learning this sort of highly nonlinear mapping is quite a challenging task, and these methods often result in meshes that don't quite align with the image content. So it might be the pose might be roughly right, but doesn't fully align with what's perceived in the image. In particular, the feet and the hand regions are often quite off. This is very common for methods. On the other hand, as we've just seen, the estimation of sparse 3D key points of people works really well if you adopt pixel-aligned representations. Those can accurately estimate the body key points in 3D as well as the 2D projections that align with the image. So we propose to use this as the input, that is, use such a key point estimator, and then reconstruct a human body mesh from the 3D key point positions alone. So not going back necessarily to the image, but rather go from 3D key points to the mesh. So here's an overview of our approach. Given an RGB image, we first use the 3D key point regressor that provides 3D positions of all the body joints. In fact, we use the method that I just showed earlier. Then comma is our method, key point aware mesh articulation, consists of a series of simple and well-defined geometric operations that articulate a canonical mesh that has skeleton to the target pose using the 3D key point positions only. So basically imagine if you have 3D key points, they are sufficient to compute the joint angles for a canonical mesh with a skeleton to pose this canonical mesh according to the estimated 3D key points. It's not entirely straightforward because we need to make sure that we deal with unnecessary twists, because those are ambiguous, right? From the 3D key points don't necessarily tell you how something is twisted or not, right? So we need to make sure we remove all unnecessary twists. But if you do that, it's very easy to get an articulated mesh just from the 3D key points. Now, while this already yields state-of-the-art, we show that these posed meshes can still be refined using sort of a simple first-order optimization that removes any remaining discrepancies between the regressed key points and the articulated mesh, and they can still be there before the optimization, just because when you pose according to 3D, there might be still some slight inconsistencies that you might want to get rid of. Note though that in contrast to all the other methods, our approach does not require training images with ground truth mesh annotations, right? All we require is a 3D key point regressor from which we pose the mesh. Now, one thing to note, we don't actually estimate the body shape, right? We only estimate the articulation of the mesh, not the body shape itself. Yet, this simple method offers significantly better alignment to the image content and achieves state-of-the-art on public benchmarks. Here's a list of methods that we compare against. Many of them do require mesh supervision, which we do not. So overall, we get better reconstruction error and accuracies. So here are a few qualitative results of complicated poses. You see the image and overlay the mesh that we've estimated. This is on MS Coco. Here is a more example where we now rotate the meshes around, so you can see how they actually look. They're very sensible meshes that we've estimated. And here are some examples running frame to frame on videos. On the left is just a basic comma method, and on the right where we do the final refinement step. And as I mentioned, these are run frame to frame, right? There's no enforced temporal smoothness at all. And again, no mesh annotations were used to train this network. Again, another example. Even though it's only frame to frame, it's temporally, surprisingly consistent. Okay, finally, I'd like to talk about global occlusion-aware human mesh recovery. So all the videos you've seen so far were basically captured by a static camera, right? However, videos are often captured by dynamic cameras, and then reconstructing a pose in a global coordinate system can enable interesting applications such as VR, animation, and sports. But occlusions are a big problem in pose estimation. And if you have a dynamic camera, there's a lot of occlusions that can happen. For instance, a person might move out of the frame, or if there's multiple people, they might occlude each other. So we would need to handle those somehow. So our goal is to estimate the pose and the shape of people in a consistent global coordinate system from videos captured by dynamic cameras. So it's a very challenging problem. Standard pose estimation methods have real difficulty with videos like this. So here's an example of our method basically from that I just presented running on this video. Estimating accurate depth, very difficult. It's very difficult to estimate the global human motion from the moving camera. And it's difficult to handle severe and long-term occlusions. And you can see at the bottom that there's a lot of jittering, a lot of weird moving of people estimated poses because the methods don't know that the camera or assume that the camera is static. So they don't know that the camera is moving. So as a result, they don't know what to do in that case. So to address all these issues, we propose an approach that leverages behavior generation models to hallucinate pose and global trajectories. So given an input video from a dynamic camera, we first pre-process the video. That is, we do multi-object tracking and redirection to obtain the bounding block sequences of each person in the video. We then apply 3D human pose and shape estimation to obtain the motion of each person, which consists of the shape and the 3D pose sequence in camera coordinates for the part of the video that a person is detected. When there's occlusions, of course, we don't know what their pose or shape is. So the motion can have occlusions where poses for some frames are missing because the person is occluded, right? So in the next stage, we propose then to learn what we call a generative motion infiller to infill the occluded parts of the video and then obtain occlusion-free body motions. Then after that, we propose to use or to learn a global trajectory predictor that infers the global route translations and rotations of each person from the local body motion. So given the infilled body motion, which is in local coordinates, we know a predictor of a global trajectory for each person. And then finally, we propose a global optimization framework that jointly refines the trajectory of each person, as well as the camera parameters to match the video evidence, such as 2D key points. And so this global optimization ensures that the spatial relationships of the people in the video is accurate and consistent temporally and globally. Now, the generative motion infiller is based on a conditional VAE. So it essentially maps body motion with occlusions and the latent code to occlusion-free body motions. And we learned this based on a data set of human motions. So it's fairly straightforward to do. So the global trajectory predictor in our approach is motivated by the fact that the body motion of a person is really highly correlated with its global trajectory. So for instance, in this video, even though the human behavior is only rendered without translation, so it's we don't show you the ground plane or anything, we can still see that the person is walking backwards, right, and then taking a step to the left. It's very obvious to us. So as humans, we can hallucinate the global trajectory taken just by looking at local body motion. So we hypothesized the same should be possible using a neural network that's trained for this task. Now, the global trajectory predictor we propose is also based on a conditional VAE. It essentially maps the collision-free body motion from the last step and a latent code V to the global trajectory of the person, including the route translation and rotations. So you really get motion, global motion out of this predictor. And then finally, we do this global optimization where we predict everything jointly. We predict the camera poses, the trajectories, all making sure that everything is consistent between people as well. So let me show you a few results here. So you see input video on the top, and then bottom left is ours, and the bottom right is sort of the state-of-the-art method or baselines. If you stitch them together, what you would get, note that the baselines aren't meant or weren't really aware of the camera motion, so they're not expected to do very well. But the bottom left is our method, and whenever one of the meshes becomes transparent, it means that we had to infill the motion because it wasn't visible or it was included in the image. And you can see that even when, sometimes the camera or the people are outside the frame, you can still estimate what their motion is. If the camera moves or stops or any of this, it's not a problem for our method. Or if they're only partially visible, we can handle all those cases and do something sensible. If you look at the top, and at the bottom again is sort of the baseline that you would get. And because we do this global optimization, at the end it's very consistent, temporally coherent. Even when there's occlusions, our infilled motions are very sensible. You can even tell that if you look carefully, you could even see that they were walking up the steps. It looked like they were walking up the steps and sitting down and so forth. So overall, it works remarkably well. Even some complicated motions like dancing, we can handle, even though there's obviously one person occluded. Right. So even something like basketball, playing basketball, works fairly well. Right. With that, I'd like to point out the additional or the work, the papers that this presentation so far was based on. So if you'd like to learn more, feel free to look at those papers. So far, the body pose estimation model only gives us the location of the wrist joint. It doesn't actually provide any details of the hand pose or the locations of the fingers and joints of the fingers and so forth. So what can we do to also estimate the pose of the hand? Well, we can basically adapt the same pipeline that we used before for body pose and apply it to the hand by just cropping out the part of the hand and estimating joint locations of all fingers and then lifting it to 3D like we did before. And that's in fact what we do. Now, slightly different than before. We're going to use two sources of training, which is just like before. However, we're going to use 2D annotations where we have 2D images labeled by hand for the joint locations. And then we're going to use 3D data, but in this case, we're going to use some synthetic data of basically an artificial hand or synthetic hand posed in 3D and then rendered and so forth. And we're also going to use some real data if we can find it. So the rest of the pipeline remains exactly the same. We take an image as input, produce a 2.5D pose. This time, that refers to the locations of the hand joints or joints of the fingers, and then we reconstruct 3D pose from our 2.5D representation and same training as before, so nothing's really changed to body pose, just the training data is different than we applied to hands. Here's some qualitative results applied to a variety of videos, and you can see it works quite nicely. There's some jitter sometimes, and we'll deal with that in a second. Here's some more results where we now visualize the hand poses in 3D, and you can see that even though the input is only 2D, the hand poses we get are actually quite reasonable. And here we apply it to both hands, the left hand and the right hand. And you can see how it also works fairly well. In terms of numbers, our approach performs favorably on several public data sets if you just apply this basic technique. Now, we did, however, notice that using the 2D annotations for our mixed training between 2D and 3D, the 2D annotations really benefit only the 2D locations, right? It doesn't help with the depth ambiguity. It doesn't reduce those. So even if we say label lots more 2D images, the 2D XY locations of the joints that are found are going to improve, but the depth for each finger will not as a result, right? Because we only have 2D annotations for those. So the question is, can we somehow improve it, even though we only have, even from those 2D annotations? Because, correct 2D pose does not necessarily ensure a correct 3D pose. So here's an example where things might go wrong. So here's 2D projection of the hand on the left, the ground truth 3D pose in the middle, and then our predicted pose with the method I just presented in 3D. And you can see that while the 2D locations are good, the depth isn't sensible. It's a very squished hand, and it shouldn't be, right? So what can we do to improve this? Well, the main idea is that we should exploit the structure of our hand, right? We know what the range of motions that hands usually can do, so we want to exploit the structural information and hopefully, as a result, improve the 3D estimation of all the joint locations. So what we propose is to add biomechanically inspired soft constraints to encourage feasible 3D poses that are sensible, and as a result, those should reduce the depth ambiguity. Now, the constraints we're going to use, they're going to be differentiable and interpretable, so we can easily include them as a loss function when training a network. And here, as an initial example, this is what you get. So in the middle is again the predicted 3D pose with the original method, but if we add biomechanical constraints, you actually get very good hand pose back that is realistic. And there's quite a bit of related work in this space. Usually this prior art also exploits this, the biomechanical structure of the hand, but typically by fitting kinematic hand via inverse kinematics. So it's an optimization-based approach, or these are optimization-based approaches that are done sort of after your initial estimate, and they're sensitive to initial conditions and sort of optimize things in isolation, not taking the image into account anymore, right? Now, in contrast, we are only using the constraints as sort of soft constraints during training, and we don't actually do it for iterative fitting as these previous works. So we model three kinds of constraints: bone length, the palm structure, and the joint angle, and we're going to directly integrate them into the training pipeline. In a bit more detail, the constraint for the bone length is to make sure that we have reasonably bone lengths for each of the bones in your finger, so they aren't too small or too large. That's going to be easily modeled as a loss function. We then also look at the structure of your palm. We do this by encouraging the proper shape of the palm by constraining the angle between the bones of the palm. And then we also look at the curvature by interpreting your palm basically as a mesh, and we want to make sure that it can only be either sort of go from flat to all the way to sort of squished together, and you can't be outside that range of curvature, which is another useful constraint. And then finally, we look at the joint angles. and we model each joint with the help of a local, or the angle of each joint with the help of a local coordinate system. And we penalize predictions that are outside sort of the valid ranges of angles that your fingers can make. And there's actually two angles. One is sort of left-right, and then up-down, which is flexion and abduction angles. And the limits are interdependent, so we can't look at them separately. We need to look at them jointly. And this is sort of the range of motions that your finger, or this particular finger, can make. And we look at the convex hull of those, and we penalize if the angle, a particular joint angle, is outside the convex hull. So it's another loss function that we add. And if we apply all those, then we get results like this, where from the 2D projection, it's difficult to get to the actual ground truth 3D pose. And our original predicted 3D pose was too flat. It had to sort of squish together, which is not realistic. And then if we add our biomechanical constraints during training, we actually estimate a hand pose that's much closer to the ground truth, and it makes sense in a biomechanical sense. And here's some more example. Again, the biomechanical constraints really help to predict more accurate 3D pose of the hand. Now, if you look at numbers, here's some ablation studies done on the front-end data set to understand the contribution of the constraints. So if we train a model using synthetic data only with full 3D ground truth, we get an error of 30.82 millimeter in 3D. If we add in 2D images, images in the wild that have 2D annotations, it helps with a 2D estimate of all the joints, which makes sense, right? Because we now have 2D supervision. It doesn't change the depth supervision very much, which is also understandable because we only added 2D supervision here. And as a result, so the 3D estimate, yes, goes down, but mainly due to 2D improvements. However, once we add our biomechanical constraints, the 2D error goes down slightly, but not a lot, right? Because that's not what it's going to fix. But the depth ambiguity is resolved much more. So the depth error goes down by quite a bit for each of the joints. So as a result, the 3D estimate goes down significantly, but the accuracy goes down goes up significantly. It goes from an error from 20.92 millimeters to 30.78, which is very good. And here we evaluated on Dexter plus object data set, and it shows that our biomechanical constraints allow us to outperform lots of fully supervised models in both real and synthetic data. And another way to look at it is that biomechanical constraints are helpful when the number of images in your labeled set is very low, right? Because when we use these biomechanical constraints during training, you basically have the number of training samples, 3D training samples that you need, which is another advantage. So if you'd like some more information about this method, see these two publications for more information. So in conclusion, I've talked about 3D pose estimation and how we can use it to articulate a human mesh, as well as how we can deal with moving cameras and occlusions, and then how we extend our techniques to also deal with 3D hand pose estimation. So thank you very much for attending my talk today.